Okay, good afternoon, everyone. Begin with chapter one. Um, I posted a few announcements yesterday. So homework one and reading assignment has been posted. So please review the reading assignment and then also look at the homework questions. We'll begin with the short introduction, not introduction. The chapter itself is just introduction. Okay, so chapter one in the book and in here is it's not very long, it's short. It's just basically the basics to get everyone up to speed. Okay, so all right, let's begin with a story about a sequence of events that came to be known as the War of Currents or the Current War. Okay. I'm assuming everybody's heard of Edison. How many of you heard of Tesla? Not the car company, the person. Nikola Tesla he was a brilliant physicist, engineer, researcher who was from Europe, I believe Serbia or somewhere around that region. He was, by all accounts, he was a genius. He could visualize things in his head. He could perform like complex calculations and far advanced of his peers. Okay, this is the late 1800s, and Edison was an established businessman. He's credited with being an inventor, but like with all corporations, he had his factories that were hiring lots of engineers and researchers, working on lots of problems and trying to market and sell them. Okay, so that's basically what he was, businessman. And one of his managers was in Europe, came across, or he'd heard of Tesla, he'd read about his work, and I wanted to meet him. So he met him, was very impressed, and he tried to bring him over to the US to work for Edison. And after some back and forth, they agreed to some terms, and then Tesla came over from Europe to the US. He worked for Edison for a while. At that time, Edison had a bounty on a unsolvable problem. So he had some prize money. It's like this is a problem in some sort of physics or some calculation that needed to be done in order to move forward with your project. And so no one was able to do that. Tesla was able to do so, or so the story goes. And so, as I said, by all accounts, he was known as a genius. He was able to solve it. And when he went to Edison to ask for his prize money, apparently Edison laughed in his face and said, "No, too bad. I was just joking. It was not real. You're my employee. It's part of your job description. You're supposed to do this." If you didn't already know, Edison was a jerk, to put it mildly. There are a few other choice words that come to mind, but to put it mildly, he was a jerk. Anyway, so they had a big falling out, and Tesla left his employment shortly thereafter. From that point on, Edison did everything in his power to denigrate Tesla and the work that he was doing. Okay. And this all culminated, again, this is a series of events that occurred. This all culminated and came to a head because at that time, mass production of electricity was just being started. Electricity, artificial man-made electricity was just being invented. Artificial in the sense man-made, not artificial, but man-made. Okay. Until then, everything that people knew about electricity was lightning strikes, static electricity. Lightning strikes, obviously, very dangerous, that occur during thunderstorms or during storms, right? So when electricity is being invented, people are fearful of it, right? So there were two kinds, something known as DC and the other known as AC. Tesla was working on AC. He believed that AC was the best way to go forward for power generation, power distribution, and transmission. He had grand ideas, and many of them are in existence today. There's like, the electric motor. Let me take a step back. No one single person is responsible for the creation, the invention of something. There's always hundreds of people, researchers that came before them, but it culminates with one person who markets it or is able to market it properly. Okay, mass marketing in a usable form. So Tesla worked on a lot of things that were worked on previously by many other researchers, like transformers, oil, stuff like that, electromagnetics. And he was a big proponent of AC. Versus Edison, who had sunk all his resources into promoting DC. So the war, or the, it culminated because they were trying dirty tricks. They were trying to show how bad AC was. They would take in stray animals from the streets and they would apply like 1,000 volts AC to them and just shock people, saying that see how AC is so dangerous. And for his own, he would promote like low voltage DC and saying DC is safe. Okay. But obviously it's not true. And this all came to a head in the World's Fair in Chicago in the late 1800s. Tesla had the backing of George Westinghouse. Westinghouse is a brand that is still in existence today. There are some electronic television sets and some electronics, consumer electronics that were sold under the Westinghouse brand name. Anyway, so Tesla and Westinghouse put forth a bid about $500,000, I believe, and said, okay, you give us this money, we're going to install, power generator, we're going to power your entire fair. Okay, this, their bid came in the lowest of everyone, and obviously, there's a lot of politics involved. But needless to say, they won that bid, and they lighted up the World's Fair in Chicago. And this was a wondrous event because until then, people had only seen light demonstrations for like, maybe in a lab, maybe in some expensive facility somewhere, but nothing like this was ever done. Okay, this is still a time when you had these poles that had gas lines running through them. So they were familiar with gas lights, like how we call street lights. There were gas lights running through the streets. So instead of street lights, the entire fair now had like electric lights. And it was an amazing thing for people. And from that point on, it was just AC just won out. Right? Edison and his engineers would try to sell DC, but AC was so easy and convenient and at far lower cost that consumers would not look at DC. He was very stubborn. He didn't want it. It's like, I cannot lose. I cannot lose. I cannot be wrong. And so he was just pouring in all his resources, but his engineers and salespeople came and talked to him. It's like, this is enough. We can't do anything anymore. It's time for you to step aside, and we have to start marketing DC because nobody start marketing AC because nobody's buying our products. Okay, and so again, as I said, that Chicago Fair, I think it's somewhere in here. Can't remember where. Was basically kind of like settle things, and then the world's first power station was established near Niagara Falls. Okay, they chose a nice round number for the voltage that would supply, which was 100 volts. They built in about 10% tolerance in it. Hence, we have 110 volts outlet today. But AC power transmission is easier if you do it at a higher voltage. The rest of the world that followed learned, and they decided to use 220 volts. So while US and North America uses 110 to 120 volts, voltage always fluctuates depending on the time of day and the generation capacity. So 110 to 120 volts. Many parts of the world, most parts of the world use 220 to 240 volts. Okay. But again, that's kind of the story that went behind. So this was, again, War of the Currents, DC versus AC. There's a movie that came out a few years ago, again, name of the War of Currents. Good movie, Nicholas Hoult and Benedict Cumberbatch. I find it fascinating to watch that. So if you have a chance, look it up sometime. Okay. Tesla's, one of the grand ideas that Tesla had was free wireless electric power for everyone. Meaning, right now, our power is not fully wireless. We have to carry around our devices, but they have batteries in them. We are carrying around our own power source, right? If it's portable, it needs to have its own power source. What he was trying to do was he'd have this tall tower, and he'd broadcast this radio waves, meaning broadcasting electrical power through the air. So you would have a device that does not have any kind of source. It simply pulls the power from the air. That was set up somewhere in New York. That is still in existence today. It's now a museum, but you can definitely look it up. He was responsible for a technology that is known as the Tesla coil, transformers, electric motor, and something that you carry around in your pocket. If you have a tablet or a smartphone that has a wireless charger, that's based on the principle, at least in part of the work that he did. Okay, the back of your smartphone has a coil, and the wireless charging plate also has a coil inside it. When you plug the charging coil using an adapter into the power outlet is converted to DC. It goes into the coil. The coil has a magnetic field. The magnetic field is floating on top of the surface of the charging mat. When you put your device down on top of it, the back of your smartphone, which has a coil, interlinks with the magnetic field of that charging mat. When it interlinks, energy is transferred between the two coils. Your smartphone or device, wireless device, receives that magnetic energy, converts to electric energy, and then charges the phone. And that's why it needs to be in close proximity, it needs to be right on top. Otherwise, it wouldn't work because the magnetic fields need to be aligned and interlinked. Okay. So that's the story, war of currents, right? I will usually like to begin with this because I find it fascinating. And then we talk about AC and DC because that's what we'll be dealing with in this class, in this course, right? So when we talked about AC and DC, what exactly is it? You've heard of AC, you've heard of DC, right? Maybe you might be fans of AC/DC. Some of you might be. But as the name suggests right here, it's alternating and direct. Okay, alternating and direct. And comes from the fact that a direct current, if we plot the value of that quantity, whether it's voltage or current, and that value remains fixed with respect to time, we call it direct current. So it's DC. It's fixed value. So the value is fixed. It does not change with respect to time. Okay, it does not change with respect to time. As you go along in your studies, you'll come across, you might already be familiar with these kind of waveforms or these kind of plots, right? On the x-axis, you have time. T is for time. On the y-axis is the value of your quantity. That quantity could be voltage, current, power, could be anything. Okay, x-axis could be frequency too, depending on what kind of plot you're trying to, what kind of information you wish to convey. But typically, most of these have time on the x-axis. Unit for time would be seconds. This is the beginning of time t equal to 0. Not really, it's not beginning of time. Time t equal to 0 for this specific purpose simply means the time or the point in time at which we begin our analysis. That's all it means. It doesn't mean anything else. Okay, it's the point in time at which we begin our analysis. That's t equal to 0. And standard numbering system. So if this is t equal to 0 right here, this is plus positive values, right? Positive values. And to the left is negative values, right? So positive values meaning this is the future, this is the past. If we begin our analysis at this moment right now, a signal that already went through is in the past. We are now analyzing the present and the future. Okay, so just a couple of things to keep in mind when you interpret these kind of graphs. So DC quantities have a fixed value with respect to time. AC variable and could take on any values with respect to time. At any given point in time, the value could be different. Okay, the value would be different. Now, we said the acronym AC and DC, the C stands for current, right? So it's sometimes, if you expand this, DC and AC, it's like direct current or alternating current. I find it funny. But in general, we never expanded it. It's not referred to as an acronym. We just simply call it as it's AC and it's DC. So we can refer to it as AC voltage, AC current, AC power, or DC voltage, DC current, DC power. Okay. All right. Now, AC comes in many shapes and sizes. Not sizes, but many shapes. You have square, rectangular, triangular, sawtooth, and arbitrary noise, etc. Okay. Any kind of signal that has a different value is AC. So far, so good. Let's take a pause. Let me know if you have any questions. Any questions? I'm assuming some of this from chapter 1, chapter 2 is covered in physics classes, a little bit. Maybe, maybe not. Some of the prereqs, okay. All right, so why is it called alternating? If it could be any random shape, why is it alternating? Well, when they first generated this AC, it was a circular structure. So it's a rotating winding. It's an electric winding that is rotating inside a magnetic field. Okay. It's a winding that is rotating inside a magnetic field. Magnetic field has poles, north and south pole. When the winding goes to the north pole, you get a positive peak. Goes to the south pole of the magnetic field, you get a negative peak. And so it's rotating constantly between north and south. The waveform goes positive, negative, positive, negative, positive, negative. It alternates between a positive and a negative value. Physically, electrons might be moving a little bit forward, moving a little bit back, forward and back. Hence the name alternating, and just AC. This is not the focus of this course. This course deals with mostly DC. We'll study AC at the end of 211. Okay, end of 211. But just to give you an idea what it means, there's a positive peak, right? So there's a positive peak right here, a negative peak right here, and then it comes back to 0. This is 0. This is positive peak. This is the negative peak. Okay, exactly symmetrical around the x-axis. So it's the waveform starts from 0, goes all the way to a positive value, comes back to 0, goes to a negative value, which is the lowest value, lowest peak, and then comes back up to 0. And from that point on, it starts to replicate itself, right? This is when it starts to replicate itself. So the point where it starts from 0 and comes back to 0 after alternating is known as one cycle. So this is known as one cycle. Each positive and negative areas are known as half cycles. Positive half cycle, negative half cycle. That's all it is. And the number of cycles that the waveform takes in 1 second is defined as the frequency of the waveform. So number of cycles per second is defined as frequency f, lowercase f. F. The unit for which was invented by the car rental company Hertz. Hence, it is named as Hertz. Not really. It was a German physicist. His last name was Hertz. Hence, it is Hertz. HZ. Okay, HZ, Hertz. So at this point, I like to ask, and this is a general knowledge question. We spoke about how the voltage in North America is 110 volts. What is the frequency that is associated with that? It's an alternating, it's an AC power outlet, meaning it's alternating. If it's alternating, it's going through its cycles. How many cycles does it go through in 1 second? It's a general knowledge question. It's not an engineer specific question. Anyone? Wild guess? Yeah, it's 60 hertz. North America, 60 hertz. The rest of the world, it's 50 hertz. I don't know why. I don't know how and why they chose that way. But it's 60 hertz. Okay. Again, remember this. This is not an engineering question. This is a general knowledge question. Anytime you plug any appliance into the power outlet, there's a label on that appliance or that power extender strip. It'll say the rating. It'll say the voltage and it'll state the frequency. If you take a look at your charging adapters, these charging adapters are like, it's a modern invention, but previously we used to have like transformers, very heavy. Now these are lightweight and you can use them anywhere in the world. If you look at the adapters, my eyes are not good anymore, so I can't really make out, but there are specifications on that. It'll state you can input 100 volts, 60 hertz, all the way to 240 volts and 50 hertz, meaning you can use it anywhere in the world. You do not have to do an electrical conversion. You only have to do a physical conversion. Previously, a long time ago, when I first arrived and traveled, we had to do a physical conversion as well as an electrical conversion. Now you don't have to anymore. You can take your current charger, go anywhere in the world, Europe, Asia, anywhere, and it'll still work. You just need the physical prongs. But it will state input 100 to 240 volts and output will be like 5 volts. Okay, 5 volts. Anyway, so it's 60 hertz, meaning, let's say one of you was Dr. Strange and you slowed down time, you stick your finger in the wall and you could feel the voltage go 0 to 110, all the way down to 0 and back to -10, up and up and up. And I'm assuming none of you are Dr. Strange, and please don't stick your finger in the wall. That was just a joke if you didn't get it. I got lots of dad jokes. All right, and it's not actually 110. There is a conversion that needs to be done. 110 is like RMS value. But again, that's for later. That's 211. That's not the analysis that we do. We are sticking with DC. But again, you keep that in mind, okay? Now, as engineers, you may have encountered, or you definitely will encounter, a wide range of values, a really wide range of values, from the very, very tiny and minuscule to the very, very large. And we use some of these in everyday life, okay? So, think you could memorize the entire table? Not really. Even I don't have it memorized. But you should definitely be familiar with the middle of the table. Okay, and we use this in everyday life. I'll give you an example. How many of you are using mechanical pencils? What's the size of those pencils? Anyone? 0.5? Anyone with 0.7? Might have seen 0.7 somewhere. 0.5 what? Anyone? 0.5 mm, millimeters. Everybody knows a millimeter, approximately this big. You have a ruler, you have a scale, 15 centimeters, 6 inches, or 30 centimeters, 12 inches, and you have a millimeter, right? Every centimeter is divided into 10 millimeters. And you have seen how small a millimeter is. If you take that small millimeter and divide it into 1,000 parts, you get what is known as 1 micrometer, which is 10 raised to minus 6. 10 raised to minus 6. And so your 0.5 millimeter pencil, or the size of the lid of the pencil, the lead, is 500 microns. It's half a millimeter, so it's 500 microns. Okay. Again, to give you an idea of how small it is, you take 1 millimeter, you divide it into 1,000 parts. Each part is 1 micrometers. This was the feature size when they first came up with microchips or integrated circuits. And so 1 micrometer is also referred to as 1 micron. 1 micron. There's an actual semiconductor company, fabrication company by the name of Micron. You may have heard of it, Micron Technologies, near Boise. That's a semiconductor technology. That's why it's called Micron. If you take that 1 micron, also, human hair is of the size of about 75 to 80 microns, very thin. Okay. If you take that micron and you divide it into further 1,000 parts, you get 1 nanometer. So unimaginable. I mean, even though I know it, I've worked with it, I still can't wrap my head around it, how small that is, because I can't just visualize it. It's impossible to visualize. Even though I've looked at it through a microscope, I can't fathom the size, right? It's 1,000 parts. So this is 1 nanometer is the current feature size of semiconductor microchips. Feature size is basically the size of the smallest feature in your chip. Okay, that's down to like 3 nanometers right now, 3 or 4. TSMC and Samsung and Intel, they're all working on feature sizes of 3 or 4 nanometers. That's small and tiny. Okay. So again, you don't have to memorize the entire table, but you better be familiar with some of these because it'll keep coming up as you go along in your career all the time. You might be in a meeting, your peer, your boss, your manager might talk about like femtofarads. Capacitances are parasitic capacitances are very tiny, typically order of picofarads and femtofarads. So that's something that you should be familiar with. Okay. Beyond femto, you could just impress somebody, right? Just say atto. All right. On the other side, we have these: kilo, mega, giga, tera, peta, exa, and you have used some of these, right? Kilobytes of data, megabytes of data, right? Your hard drive is 1 terabyte, 4 GB RAM. 4 GB RAM is basically 4 gigabytes of RAM. So 10 raised to 3, 10 raised to 6, 10 raised to 9, 10 raised to 12, and so on and so forth. Data sizes now are huge. Data centers probably are dealing with like exabytes and even zettabytes of data. Huge. Okay, so as an electrical engineer, you might come across, if you go work for a company, might be working with like tera and petabytes of data. So that's, again, something you could be familiar with. Just to show you, as an example, how much is 1 million? How much is 1 million? 10 raised to 6, 1 mega. So, as a wild guess, how much is 1 million seconds in days, weeks, or months? Wild guess. And 1 hour is 3,600 seconds. You have 24 hours in a day. How many days, weeks, or months do you think 1 million seconds is? Wild guess. 5 days, 10 days, 20, 30, 40 days, 100 days. Feel free. There's no prize or penalties. 30 days. I heard 30. That's a good guess. Not quite. Anyone? 7? 27, that's another good guess. A week, yeah, 7 days. That's by far the closest. It's approximately equal to 11.3 days, or 11 point some number. Okay, days. That means if you had $1 million and you spent $1 every second, it'll last you less than 12 days. Now, just to give you the scale of the economy that we talk about, how much do you think is 1 billion seconds? Days, weeks, months? Huh? 5 years? Student in my previous class said 11,000 days, which I mean is technically correct. But the whole point is we don't want to say 11,000 or 11. We come up with terms and words, right, for that. If a person had $1 billion and they spent $1 every single second of their lives, it would last them more than 31 years. 31 years. They've been following the stock market recently, how it's crashing. It says it lost $2 trillion. So if we add 1 trillion seconds, that would be 31,000 years. Okay, that's a huge number, right? When you put in terms of time, it hits the magnitude and the value. Oh, on a slight tangent. Anyone ever see the movie called In Time? Came out a few years ago. Justin Timberlake, Amanda Seyfried. Cheesy sci-fi kind of futuristic movie, but I really enjoyed it. The premise of the movie is that there's no currency anymore. The currency is time. Everybody in that world, dystopian world, grows until the age of 25, and then they stop growing. And there's a clock count on their hand, and that clock starts. And so most people have only like a day to live. When the counter goes down to 0, they die. Okay, so the premise of the movie is that the poorest of the poor people who, we live paycheck to paycheck. So it means they work, they make just enough time to live for another day. And the richest of the people had like thousands of years in their hand. And so again, as I said, corny maybe for some people, but I really enjoyed it. So if you get a chance, look up that movie called In Time. I know some of you are looking it up right now. All right, UniPrefixes. I don't have a particular enlightening talk about this. I just find it particularly funny because we are going to be studying electric circuit analysis. We'll work with conductors, resistors, capacitors, and inductors. Actually, not capacitors and inductors. We'll pretty much work with just resistors. 211 is when you'll work with a lot with capacitors and inductors. Okay. So I like to say, don't worry, Thor is here to help. I don't know how he's going to help. Our focus is primarily on resistors. And this is 211. And this is 306. Okay, this is 113. All right. So electric circuit, what time is it? We have 15 minutes. What is circuit theory, right? Well, what is an electric circuit, first of all? What is an electric circuit? Talking about electric circuits, so what the heck is it? Anyone do the reading? If you read the book, might be able to explain. Okay. So electric circuit is nothing but a mathematical model of an actual physical system. Okay. It's a mathematical model of an actual physical electrical system. That's what an electric circuit is. It's a mathematical model, right? And then circuit theory is basically a case or a subset, I wouldn't say a subset, but a way of calculating this. So it comes from electromagnetic theory. Okay, the book describes it as a special case of electromagnetic theory. Now, I don't know about you, but electromagnetics are not my idea of a good time. As a student, I didn't like it at all, but it's very essential. Understanding of electromagnetic theory is very essential. You will learn about that in your 200 level and 300 level classes, okay? And also in physics, obviously. So if you have such a model, it allows us to calculate, so analyze, to calculate, and to predict the behavior of that system, okay? Right? So again, circuit analysis or circuit theory is basically electromagnetic theory, but we do not want to apply the generalized equations because they are very complicated. They require advanced mathematics. And so the circuit theory was developed where we can perform linear analysis on these circuits. Okay. There's a mathematical model for mathematical calculations, okay, of an actual electrical system. But in general, when we say electric circuit nowadays, electric circuit refers to like an actual system, and we also refer it to the model, right? We can say the electrical circuit in this room has some issue, or the electrical circuit is really wired great. Or we could also say, okay, this circuit diagram is for an electric circuit, right? So it refers to both the model as well as the actual system in real life. And then, of course, circuit theory, as I said, is the study, and it's a study of electric charges. Okay. It allows us to perform analysis and calculations. Electric charges are basically charges that are moving inside a system. Now, when charges move, it's going to affect the components in the circuit, right? And so every component, every wire, every conductor, every resistor, capacitor, any component in the circuit will respond to that charge. Now, charge is propagating. It should take some time. It's not instantaneous, right? Thanos cannot snap his fingers and just wipe everything out like that. That's just fiction. It takes a finite amount of time. Even though it's a finite amount of time, it's very, 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 very quick because it happens nearly at the speed of light, okay, which is 3 × 10⁸ meters. Okay, very quickly. So if the circuit is small enough, that it can propagate very quickly. So the propagation is fast enough to negate the distance in the circuit. We can assume that the effects happen at a near instantaneous time. Okay, it happens near instantaneously. So if that happens, we can lump everything together and perform one analysis. And we can state that is a lumped parameter model or a lumped parameter system. Okay, and so that is one of the assumptions we make right at the beginning of our journey as an EE, as an electrical engineer, that this is a lumped parameter system. Everything that we deal with in this class, in this course, and future courses also, is a lumped parameter system. The effects of a energy source being applied happen near instantaneously. Okay, so in that case, we are saying that we snapped our fingers, we flipped on the light switch, and it happened instantly. Okay, but it doesn't happen instantly. It's a finite amount of time, but we assume that it's near instant. All right, let's take a pause. Let me know if you have any questions. All right, what time is it? Okay, we have time. So far, so good. Okay. So the key word was the system must be small enough. But small is relative, it's subjective. What is it small compared to? So the comparison is, again, lump parameter system, effects are instantaneous. Oh, by the way, if you have trouble reading my chicken scratch, just let me know and I'll repeat it. Instantaneous. All right. So system must be small or small enough. Okay. Excuse me. All right. So what is small? It will be small compared to the wavelength of the signal. Compared to the wavelength. Okay. Wavelength is basically the distance between the waves when it starts repeating itself. That's the simplest statement. Mathematically, it is represented with the Greek letter lambda. It's like an inverted Y. Have you come across this before? Perhaps in a physics class. Lambda is equal to anyone? C over F, where C is used as the speed of the signal, and we use that as speed of the light. Okay, it may or may not be quite as fast as speed of light, but for all approximations, that works. So C would be 3 into 10 raised to 8 meters per second. Meters per second. 3 into 10 raised to 8 meters per second. Oh, one thing on the previous slide. Right here. No, right here. I said frequency is the number of cycles, alternating cycles in 1 second, right? That's the frequency of the waveform. But that one cycle, basically it's after it's done, it repeats itself. So that is also known as the time period of the waveform. The time period of the waveform. And it is noted by a uppercase or capital T. Capital T unit, standard units, seconds. Seconds. It's capital T. Lowercase t is the time as a variable. Uppercase T refers to time period of the waveform. Okay. And the relationship between time period and frequency is that they are inverse of each other. They are reciprocals of each other. So T is equal to 1 over F, or F is 1 over T. So again, T is the time period. It's the reciprocal of the frequency. So the higher the frequency, the lower the time period. Do you think 60 hertz is a high frequency? So it goes through multiple, 60 times in 1 second, right? I thought so too when I was a student. If you think about it, what is normal human hearing range? Typically, it's 20 hertz to 20 kilohertz. I could probably not hear above 15 getting older. Anyway, so normal, they say it's around 20, 20 to 20 kilohertz. So 60 hertz is very, 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 very low frequency. So when I was a student, it's like, yeah, 50 hertz, that's a large number. And then then they explained, it's like, okay, normal hearing range is like 20 hertz to 20 kilohertz. So 50, 60 is like way at the bottom. Most sound effects in movies, the thumping noises that you hear, are basically around 100 or between 50 or 100 hertz. So a really good subwoofer, then you can feel the sound vibrations, but you may not be able to hear it. That happens. So yeah, it's a very low frequency. As an example, you use very, very high frequencies every single day. Your CPU speeds, motor, sorry, not motor, the whether it's a laptop or a desktop or your computing systems, the CPU in there has a clock frequency. That clock frequency is at least 1 gigahertz. 1 gigahertz is a high frequency. Microwaves, cordless phones operate as 2.4 gigahertz. Your wireless band of your routers is 2.4 gigahertz and 5 gigahertz. So we use those high frequency signals every single day. Anyway, coming back to here, we just have 2 minutes left. So if you have to leave at 4, you can leave. I'm just going to record for like one more minute. Actually, there's a next class coming, so we can't delay. All right, so let's say as an example, frequency is 60 hertz. Right? Example, 60 hertz. So if you calculate this, lambda will come around to 5 into 10 raised to 6 meters. So wavelength of such a system would be 5 into 10 raised to 6 meters. To be considered small in relation to this number, let's say we take 10% of this number. So small is relative. Small could be approximately 10% of this number, or 0.1. Right? So 0.1 is 5 into 10 raised to 5 meters. It's approximately equal to 300 miles. Right? So for all purposes, if you're just using a 60 hertz system, then 300 miles, anything smaller than 300 miles is a lumped parameter system. I wanted to do this, but that's fine. We're just leaving. This is just an approach to problem solving. So we'll end class here today. We'll pick up here again on Monday. There'll be a very small quiz on Monday based on what you've done here and based on homework 1. So again, reading assignment and homework 1. Please check Canvas and complete those. I will be available over the weekend. If you have questions, send me an email. If you want to meet on Zoom, I can do so on Sunday. But just let me know and reach out. All right. Have a good weekend, and I will see you all on Monday. All right.